basically 5 numbers that I'd like you to know for IR. Again, because we're an open book, open note land, there won't be any sort of memorization, I guess. But if I would have you memorize, I would have you memorize these 5 numbers. These are the 5 numbers that I know. And then we can kind of shape them a little bit and go up and down those little 5 tent poles. So 3300, that is where you're going to see OH and NH. And they're going to stick out like a sore thumb. In fact, they're going to look a lot like a thumb because they're going to be broad due to hydrogen bonding, right? So if you think about, if we're looking at bond strengths, then these strengths are all going to be varied by how strong hydrogen bonds are to those other H's. And so generally speaking, on the left, the extreme left of your IR spectrum, if you see a big broad peak like that, that is definitely an OH, definitely an alcohol. If you see a slightly narrower peak like that, especially if it has a fang, I like to call it a fang, that could be an NH. Again, NH hydrogen bonds, but not quite as well as an OH bond does. And sometimes if you have an NH2, you'll see kind of 2 fangs like that because you've got the 2 different stretching combining with each other. So OH and NH broader than usual. OH is broader than NH. NH can give you kind of 1 fang or 2 depending on whether you have an NH or an NH2. As an easy rule of thumb for CH stretches, 3000 is a really useful dividing line. It just so happens that sp2CHs are usually right above that line and sp3CHs are right below that line. So again, sp2CH would be like on a benzene ring. Hydrogens like that would be slightly over 3000. Simple methyl, ethyl, etc. would be slightly under 3000. Again, most compounds you're going to see have some kind of CH. And so we're usually going to see some peaks around 3000. They're going to be a lot sharper than OH because they're not hydrogen bonding. And they're going to be a lot smaller too because the CH bond is a lot less polar than OH and NH are. There's usually a big gap in an IR spectrum between 3000 and 1700. If there is something in that gap, it's probably triple bonded carbon. So CC triple bond around 2100, CN triple bond, a little bit stronger bond, a little bit higher frequency, 2200. One thing I should have put up here, an alkyne CH is actually quite high. It's around 3300 wave numbers. Again, it's a higher wave number than that because it's a stronger bond. Remember, sp carbon makes a stronger bond to H because it's got greater S character. So if we see a sharp peak out among where we expect broad peaks, that sharp peak is going to be an alkyne CH. The easiest thing besides an OH to pick out of an IR spectrum is the CO double bond, carbonyls. Carbonyls are going to show up around 1700, maybe a little bit higher for ketones and aldehydes, but they're going to stick out like a sore thumb because that's a really polar bond, right? The CO bond is very polar, so it's strongly absorbing. So it's going to be the tallest peak in the spectrum that you're seeing, okay? Esters are going to be a little bit higher than 1700, approaching 1750, so 1735 to 1750 in there somewhere. Amides are going to be a little bit lower than 1700, so around 1650 or so, 1650, 1675. Why is that? I think that has to do with resonance stabilization. That lone pair nitrogen is really pushing into that pi bond. In general, if I have a pi bond conjugated to that CO double bond, I'm going to see the conjugation get lower for that ketone by about 25 to 50 wave numbers. And that's for ketones, esters, for all of these, and for the alkenes, right? So conjugation is going to lower these frequencies. Why? Well, because we're building in some of this resonance structure character where there's not really a pi bond there, right? So by spreading out electrons, we make this sort of less of a double bond, and so we have a lower frequency. Carbon-carbon double bond, a little bit weaker bond, a little bit less polar bond. So it's going to be a lower frequency and it's going to be a shorter absorbance. If it's not conjugated, so if it's just kind of double bond on the end of something, we're going to see a peak around 1660 wave numbers. But just like the CO double bond, conjugation is going to lower that frequency. So if I have two double bonds together like this, even if this is a CO double bond, like in my previous example, then you're thinking more like 1620 to 1640 range. And benzene itself, kind of the epitome of conjugation, way down 1600. And this is about the lowest frequency peak that we care about in this class, us together, you and me, right? Other people care about peaks smaller than that. Usually, once you get it below 1500, we call that the fingerprint region for two implications there. A, yes, it's kind of complicated. There are lots of combination and benzene stretches, and so it's not easy for us to get information from that. But also fingerprint in the sense that even very similar, but also a fingerprint in the sense that it's kind of unique for each compound, right? And every compound is going to have its own fingerprint combination of peaks in that range. So for our purposes, we're usually going to stay above 1600 to identify functional groups. But people who really, really care about IR and can dig into it can get information below 1500. So this is your list, right? Again, 3300, broad NH and OH. 3000 is that dividing line between sp2CH and sp3CH. Kind of a no man's land around 2000, but we might see triple bonds there if they're there, and if there's any kind of dipole there, right? If it's a perfectly symmetrical molecule, you might not see that peak because there might not be a dipole there. 1700, any number of carbonyl or carboxyl compounds, all of which we can name now. What's up? 1660 CC pi bonds. Again, both of these will get lower if they are conjugated. And then under 1500 fingerprint region, we're probably not going to dig into that too much this class. Okay, so now that we have this list, we'll spend a lot of time just kind of practicing trying to interpret spectra.